All right, welcome class back to another fun video while we are on our field trip in our backyard today with To the Moon and Back. Today we are going to be talking about some of the different laws that are always applying to rockets while they're flying in the atmosphere and as well as in space in the vacuum where there is no air or friction. And so we're going to be talking about Newton's laws. And before we get too far, my name is Will. We all know me. But I also have my lovely, fantastical assistant over here, and this is Sean Pill. So everyone say, hello, Sean Pill.
Hello, Sean Pill.
Hi guys, how are you doing today?
Excellent job. So we're going to go ahead and hop right into our first law that Newton came up with. And how it reads is the object at rest will stay at rest. So let's see how that works out. I've got an 8-ball right here. It is an object, and is it staying at rest?
Yes, it is staying at rest.
It is staying at rest. Now, let's go ahead and read the rest of it all over again. Object at rest will stay at rest. Object in motion will stay in motion until acted upon by another force. So, we have that object staying at rest. It looks like it's in rest. What do you think, Pill?
I believe it is in rest.
Excellent. Now, let's see what happens if we push it forward, if it will stay in motion. It looks like it's staying in motion. It's slowing down just a little bit. Now, why is it slowing down a little bit? Because Newton says that it won't slow down and it won't stop until another force acts on it. So what is actually slowing our 8-ball down? Eventually it's going to stop. So that means that Newton's law isn't really a law. But that's because we're missing one key concept. And that concept is friction. And the resistance to motion of an object moving relative to another. What's happening as this 8-ball moves across is that the friction of the carpet is slowing it down. If we were in the vacuum of space and we threw this 8-ball in space, it would continue to travel forever and ever and ever, and it would never, ever stop. But if it was stopped, it would never move. If it was moving, it would always be moving.
And that, guys, is Newton's first law. An object at rest will stay at rest. An object in motion will stay in motion until acted upon by another force.
Now, we here are lucky enough to have friction down here on Earth because there is always the air. So even if I were to throw that cue ball across a room, it will run into air. All this air that's around us that we can't see, but it's there. And so we're going to go ahead and use Newton's first law to show you kind of how a parachute uses that concept to slow it down. So, what is a parachute trying to accomplish? It is a device used to slow the descent of an object so that it safely stops. All right, it's moving an object from motion to rest. All right, so we're gonna go ahead and turn on over here. We've got this nice ladder that my assistant is going to hold for me. Going to climb on up to almost the top, but not quite. But we're gonna go ahead and see how my parachute that I constructed out of a plastic bag from the grocery store, and I just tied the strings to a water bottle. I'm gonna throw it on up. It's kind of windy right now, so I think I'm gonna throw it up that direction and see if maybe we can get some. Ooh, we can already see it's kind of working just with the wind. So I'm gonna throw it up that way, and let's see if it can slow the object by using friction. There we go. It worked pretty good. Let's go ahead. Pill, why don't you grab that? Let's see if we can do it one more time. This time we're just going to drop it. So the bag right here is catching all of that air, which is causing friction and air resistance so that it slows it down. There we go. All right, now we have another way to kind of demonstrate how this is working out. Go ahead and grab a piece of paper.
So the way this works, guys, is that we can actually see a lot of the air resistance in the air just using one piece of paper. So when I drop this piece of paper, look how slow it's going to fall to the ground.
The air gets in its way, it causes friction, and it pushes it all over the place. But if we go ahead and put that piece of paper still on a flat object and we drop it, it goes straight down because there isn't enough air resistance to push that cardboard out of the way and have it work the way it was working just before.
So let's go ahead and demonstrate that one more time. We have the paper by itself, flopping around in the wind. Let's go ahead and drop it. And it goes down nice and slow. I think that might have taken 2 seconds. So now let's try this one. And without that air resistance, it falls a lot faster.
Excellent. And that's kind of how that parachute is working. It's getting all that air resistance by its big bag, catching all that air and going down. Would a parachute work on the moon? That's a good question. Think about it.
Is there any air on the moon?
There is not. The moon does not have an atmosphere, so it wouldn't really work. And so that's why we had to use rocket engines to land on the moon. All right, let's go ahead and talk about our second law. Back on over here. We have law number 2. The heavier an object is, and the faster it is traveling, the more force it exerts. So what is force? Force, on over here, we can zoom on in nice and close. Force, any interaction that changes the motion of an object. So we're gonna go ahead and try the force out on 2 different objects. We're gonna drop these into some water and see which one exerts more force. This squishy, bouncy kind of ball, or this clay cue ball. All right, we've got 2 buckets of water. Now, we are gonna drop this first one right here in this first bucket of water. And actually, let's do the foam one first. Let's see how much force it exerts on the water because it's gonna be changing the direction of the water. Right now, the water is at a still, it's resting. It's not moving, it's not going in any direction. And what we're gonna have is we're gonna have something come into contact with it and it's gonna start moving it around. And the heavier it is, according to law 2, the more it's going to push it out of the way. So let's see what happens. Here we go. 1, 2, 3. We got a little bit of a splash, but not too much. We're gonna go ahead and do this other one about the same height. It's much heavier. It's a little bit smaller, but it's still heavier. Let's see what we get. 1, 2, 3. That was a much bigger splash. Now we're gonna try those again, but we're gonna do a close-up just right here and just right there. All right, so bring that camera right in here. All right, that first splash with the orange squishy ball, Try to see how high that water gets. All right, 1, 2, 3.
Just a little bit of a splash.
Just a little bit. All right, now we're gonna move on to the other one with the heavier cue ball. 1, 2, 3. Woo, there we go. That was a pretty good one. All right, now, the other part of Newton's second law isn't just how heavy an object is, but also how fast it is going. So we're gonna go ahead and we're gonna get on this ladder so we can get a little bit more elevation so that when the balls hit the water, they're traveling faster. Now when we do this, they should both have a higher splash rate because there's more force being exerted. All right, so 1,
2, 3.
There we go. That was a little bit bigger. Let's go ahead and pan over to the other one now. All right. 1, 2, 3. Woo, that was a big one. That was a big one. Let's see if we can do both of them at the same time.
Get real nice and close for this one.
Here we go.
1, 2, 3.
There we go. Oh, we even lost some water on that one over there. Excellent, excellent job. All right. Now, just because I really, really want to, I want to test Newton's law out. Something that's moving faster is going to exert more force. So I'm going to go ahead, I'm going to get on top of that ladder, and I'm going to throw it down at these buckets of water and see how much of a big splash we can get with both of them. So I'm going to go ahead and start with the foam ball, and I'm going to throw it as fast as I can. I'm hoping that the resistance in the air doesn't stop this one and push it out of the way because it's so light, but let's see how much we can get. Here we go. Oh, missed it. Let's try again. That was a bounce. 1, 2, 3. There we go.
That was a good one.
That was a real good one. All right, now we're going to go ahead and do the other one. 1, 2, 3. Oh,
That one didn't bounce.
that one didn't bounce. All right, second attempt. 1, 2, 3.
Woo! That was a lot of water.
There we go. All right, so let's go back to law number 2. Zooming right nice and close. The heavier an object is, the more force it's going to exert. That's why the cue ball pushed and made a bigger splash. It had more force to exert. And the faster it is traveling, that's why when we used the cue ball and I threw it, it made a bigger splash than when I just dropped it because it was traveling much, much faster. All right, now we're going to go on to law number 3. For every action, there is an equal and opposite reaction. So for this, we're going to pan on out. And what we're going to do is we're going to watch this cue ball, and it's going to run into the side over here. And what do we think is going to happen? Remember, for every action, there is an equal and opposite reaction. Here we go. So the opposite reaction is that it bounced the opposite way after it hit something. Let's try again. And again. And again. And again. There we go. Excellent, excellent. That is a little bit of a demonstration of law number 3. Now, we're going to kind of put all of these laws together in this next concept, which is right here. Conservation of energy. Energy can neither be created nor destroyed, only transferred. So we're going to pan on out. So, energy, it can't be created. All of the energy in the whole universe is just here. It's existing. We can't make any of it, and we can't destroy it. We can only transfer it from one thing to another. So what happens when I take this one cue ball, the 7, and I throw it and smash it on the 4? Is it going to destroy the 4? Is this energy that this 4 has going to disappear?
No.
I don't think so. Not according to the conservation of energy. So what happened? Let's go ahead and do this so that we can see where the balls go. Go ahead and let's pan on out. It transfers. All of the energy from the 7 is transferred to the 4. Maybe not all of it, but a lot of it. And that's why the 7 will slow down. Watch, it slows down. And the 4 is going to go from rest and start speeding up. Look at that. The 7 is almost perfectly still, and the 4 is still moving. All right. Now, we're going to test that one more time here. We're going to put one of them here. We're going to have this 8 ball. And if my lovely assistant, he's going to go ahead and take that 8 ball, and he's going to smash it into the 7 while I hold it. And we're going to see, will the energy transfer from the 8 ball into the 7, and then into the 4. Look at that. The 4 is still moving. All right, let's try it one more time in slow motion. 1, 2, 3, 4. There we go. Look at that. Still going. Excellent. And that's because the energy from the 8 transfers into the 7 and keeps going into the 4. Now, I want to go ahead and use the rest of the balls we have and transfer them all into here. So let's go ahead, let's pull some out. Let's see what happens when we get a whole bunch of them in here. All right, will my lovely assistant go ahead and show us the conservation of energy, the transfer of energy from one to the rest. That was pretty good. Let's try that again. There we go. That 3 is still moving. There we go. Excellent. That's the conservation of energy. Now, our homework for today is going to be the parachute. And so what you're going to have to do is you're going to create your own home parachute so that we can use some of these laws so that we can bring an object from moving to rest. So you can use any kind of plastic bag, trash bags work, because they catch all of that air. Instead of using a water bottle, maybe you have a Lego figure or an action figure or a Barbie or anything like that. That can be your weight down at the bottom, kind of like an army man, para-jumping into a situation. Whatever you want, and go ahead, make it, test it out, and then take a picture of it and send it back to me. As far as that is, that's all we have for today.